Welcome. My name is Jerry Lynch. I'm the Donald Malloy Department Chair of Civil and Environmental Engineering here at the University of Michigan. I'd like to welcome everybody to our lecture series this afternoon. Our distinguished lecture series actually begins in 2017 when our department undertook a multi-year process of strategically planning what the future of our profession and our department would look like in the foreseeable future. In 2019, we completed our strategic vision, which included 5 strategic directions that we felt defined where our field will be going towards to have continued impact on our society. Those 5 directions are human habitat experience, looking largely at the interface between infrastructure and the natural environment and the impact that they have on humans and their experiences in both of those environments. Shaping resource flows that looks at how do our resources flow through our society and how does that lead to a more sustainable future for our habitat. Adaptation, which is looking at how do we adapt our infrastructure and the way we manage our infrastructure and built environments to address some of the changes we're seeing, such as those induced by climate change. Autonomy, looking at how does automation of our infrastructure and the automation of infrastructure services changes how we essentially service the needs of our society and ensures our society is resilient. And then finally, smart infrastructure finance, which is looking at how do we finance our infrastructure going forward? How do we address the existing finance gaps that exist in the infrastructure space? And how do we generate new forms of revenue that we can reinvest into our infrastructure renewal for the future? So this is a very exciting vision for what the future of civil and environmental engineering may be. And it's an exciting vision of how our department is going to shape the future as professionals in this space. It really, in many respects, reaffirms our commitment to essentially serving in the best interests of our society and ensuring that our society continues to have a high quality of life. The lecture series that we have today, the Building Future lecture series, really highlights this vision of the future. This specific lecture series is designed to provide a forum for us to discuss each of these different strategic areas. And today, the strategic areas shaping resource flows will be in focus. The lecture series aims to build a broad community that includes industry professionals, researchers, educators, students, policymakers, a whole group of stakeholders that are fully engaged in these topics. We're also aiming to break down traditional barriers that may exist between the laboratory and the field and really aim towards accelerating our research and our knowledge into practice. So in order to get here, there's a number of people that made this event possible, and I'd like to acknowledge their efforts and their support. So a big thank you to the co-sponsors of this event, which includes the Center for Low Carbon Built Environment, the Global CO2 Initiative, the American Concrete Institute, and the City of Ann Arbor. I'd like to also thank the Strategic Implementation Committee that's been led by Professor Sang-Yoon Lee here at the University of Michigan. Also, I'd like to thank Victor Lee, who's the James Rice Distinguished University Professor of Engineering, as well as the Benjamin Wiley Collegiate Professor of Civil Engineering here at the University of Michigan. Professor Lee has agreed to serve as the panel moderator. Before turning it over to Victor, I'd like to just say 2 announcements. The first is one focused on accessibility. We want to make sure that our event is accessible to all the participants that are looking to join us today. So this webinar will have a live automated captions and a transcript will be available after the presentation. So you have the option to choose your viewing option. So in your screen, you can click live transcript on the control bar at the bottom of your screen, where you'll be able to show or hide the subtitles and view the full transcript of today's lecture and panel discussion. So without much further ado, I'd like to introduce my colleague, Victor, who will take it from here and introduce our speaker and our panel. Victor?
Okay, thank you. Thank you, Jerry. I'd like to welcome everybody participating in today's event. Today's distinguished lecture emphasizes the strategic theme of shaping resource flows. To give an overview of this theme, I would like to play a 2-minute video.
Historically, we've pulled resources out of the earth, and then after we're done with the resources, we would release it back out to the environment. We started to realize that a lot of those wastes that we would release have valuable resources in them. Civil engineers and environmental engineers were designing a lot of those flows. And so I think we have a big role to play in how we might continue to shift the mindset and think about, the future of what those flows might look like. One of the things I think we're doing that's really special is separating our wastewater right at the source, right at the toilet. And the reason that we're doing that is we can pull the nitrogen and the phosphorus out much easier before it's diluted in the wastewater, and then convert that nitrogen and phosphorus into really valuable fertilizer products. Researchers in CEE are building RECO blocks. These are blocks built out of materials from carbon that's been sequestered that are used to build structures. And then when the structures are done, rather than landfilling the material when we tear it down, we take those blocks and we use it in new buildings, shaping the flows of these resources rather than a linear flow. We're making this a cyclical flow. In 50 years, if we're successful, this is just going to be in every activity we do as a civil and environmental engineer, how we're getting our resources, what we're doing with the resources, and where they go when we're done with them is going to be ingrained in our work.
All right. During the lecture and panel discussion, I would like to invite participants to send in questions using the Q&A function. We'll try to get it to as many of the questions as time allows. Now, I'd like to introduce our very special speaker and panelists. We're very fortunate today to have Bruce King, who will speak to us on building a climate solution. The presentation by Bruce will be followed by a panel discussion with three distinguished panelists, Dr. Missy Stutz, Lionel Lemay, and Dr. Luca Henrion. Bruce King is the founder and director of the Ecological Building Network and author of the New Carbon Architecture. He's also the author of the ASTM Standard on Urban Construction, and most relevant for today's conversation, the Marin County Low Carbon Concrete Code. Dr. Missy Stutz is the Sustainability and Innovations Manager for the City of Ann Arbor. In this role, she works with all city operations, residents, businesses, the University of Michigan, nonprofits, and others to make Ann Arbor one of the most sustainable and equitable cities in America. Lionel Lemay is the Executive VP, Structures and Sustainability for the National Ready-Mix Concrete Association. He leads a team of professionals to offer building owners and designers cost-effective, durable, and sustainable concrete building solutions through education, research, and design assistance. Dr. Luca Henrion is a research fellow for the Global CO2 Initiative at the University of Michigan. He is a scholar in the field of carbon management, focusing on assessment of carbon capture and utilization policy impacts on climate solutions. As you can see, we have deliberately arranged to have representatives with government, industry, and academic perspectives. The construction landscape of our built environment is complex, with stakeholders ranging from financial institutions to developers, builders, public and private owners, the AEC community, material suppliers, and now industry byproduct providers. And I use the word byproduct instead of waste stream, precisely because of our desire to repurpose these byproducts, such as fly ash and carbon dioxide, and utilize them as valuable resources for our built environment. This brings us to today's distinguished lecture. Let me now invite Bruce to speak to this theme and give his presentation. Bruce?
Thank you. Okay. You all can see that then?
Good.
Good. Well, thank you, Professor Lee and Professor Lynch and everybody at the University of Michigan. Thank you very much. This is an honor and a pleasure to be here. And I should add to my biography that what Professor Lee didn't mention is I've actually been a practicing structural engineer for 42 years. So I know a little bit about what I'm talking about here. But I do want to talk about buildings as a climate solution, a rather exciting new thing that's arriving in the world of green building and more broadly in the world of construction. And let's start with a metaphor. Some of you may have seen the movie Apollo 13, great movie, Tom Hanks, I don't know, 15 years ago or something, based on a real life event in the early 70s. One of the early lunar missions had a problem. On their way out to the moon, they realized that they were leaking oxygen. They weren't going to be able to complete the mission and land on the moon, so they had to sail on around the moon and get straight back to Earth as quick as they could, which they managed to do. And they were on their way back to Earth when they realized that they had another problem. The astronauts were sitting there in their capsule, 3 of them, breathing increasingly low oxygen air and exhaling CO2. CO2 will kill you if it builds up enough. They were going to asphyxiate in their own exhalations before they got back to Earth, which led to this epic moment that I call the Geek's finest hour, where the mission commander gathers all his engineers in Houston, dumps a big box of stuff on the table, and says, you have an hour to figure out how to make a CO2 filter that those guys can make in the capsule. This is all they have in the capsule. This is what you have to work with. Make a CO2 filter or they die, which they did. And the metaphor gets even better because the astronauts in the capsule are getting sleepy. The asphyxiation from CO2 will diminish your cognitive function. So they had to not only invent a CO2 filter, but communicate to an increasingly basically dumb audience to make. But they did succeed. It's a great story. It's a cool movie. Anybody spot a metaphor in there? This is how big our atmosphere is. If you scraped it all off the surface of the planet, it would be about this big. It's about 5-6 miles, about the distance from Battery Park to the middle of Central Park in New York. I'm sure there's something comparable near you. It's less than the distance across San Francisco is how thick the atmosphere is, where all the air is, where all the potable water is, where all the life is. It's really extraordinarily fragile. That's what we're working with here. In the 500,000 years that our species has been evolving away from the primate tree, the CO2 in the atmosphere has been bouncing back and forth between 200 and 300 parts per million. I'll bet all of you already know all this stuff, but it bears refreshing. And since the dawn of the Industrial Revolution, when we started burning fossil fuels, but especially since World War II, it's shot up past 400. Here's the interesting thing. If we somehow, by some miracle, could stop on a dime tomorrow, burning all coal, oil, and gas, the CO2 would still go up. The methane being released in the Arctic, the reduced albedo on the snowfields, et cetera, we'd still have a big problem. We have to draw it down. We have to get the global warming gases out of the air. And I specifically use the word drawdown because if you don't know about the book Drawdown by Paul Hawken, came out about 4 years ago, the 100 easiest and most technologically accessible solutions to climate change available to us. It's full of surprises. It's a very interesting read. It's how we can actually turn this thing around and bring the carbon back home, to put it poetically. One way to do it is the oceans. They're doing the job right now. By default, the oceans are absorbing the excess carbon dioxide in the air, which in a way is nice, but in a way is not nice. It's acidifying the ocean. It changes the pH. It's melting the coral reefs. It's bad for a lot of the life in the ocean. Another place to put it is soil, and there's a lot of people working on how to do that. We've basically decarbonized a lot of the agricultural soil all over the planet by the way we grow food, tilling it and turning it over and releasing methane and changing the way the soil works. So there's a big turnaround in progress there with the farming community, and a whole lot we could say about that, but I'll leave it at that and just say that buildings are the other big sink that we have available for putting the carbon We can put it underground. There's problems with that, but buildings are a big one. By far the biggest artifact of human beings on Earth are our buildings and our cities, our infrastructure, all of that. And there's a lot of it. We're building the equivalent of another New York City every month right now. And that might not seem credulous to you in Michigan or here in California or anywhere in North America, because it's not happening here. It's happening in the Southern Hemisphere. It's happening in China and India and places like Cairo that I visited a year ago, where a city of 5 million went to 25 million in a couple of decades. And it's a huge expanse of nothing but concrete and brick all over the desert. I never saw a shred of insulation in the week that I was in Cairo. And there's many, many cities like that all over the world now. Here's some basics. Hang on a second, I gotta adjust this Zoom thing. There we go. Buildings account for about 40% of our emissions globally. You can change that number up and down, but that's the number most people agree on, 40%. Where does it come from? Well, any building project has two phases. You build it, those are the embodied emissions that go along with the construction process and all the trucks roaring around in the manufacturing processes and whatever goes into making all the materials. And then there's the operating emissions from running the lights, running the heater and the air conditioning and all of that stuff over the lifetime of the building. And over the lifetime of the building, operating emissions typically dwarf the embodied emissions, far, far bigger, over 60, 80, 100 years. And so that's what we've been focusing on in the 30 years of the green building movement, is reducing those operating emissions to much lower, even net zero, as you hear people talk about. But here's the thing. We can't think about 60, 80 years. We have to think about the next 20 years because we are in climate emergency. What can we do right now? This is triage. And when you look at it through that lens, when you look at it from that perspective of the next 20 years, it changes quite a lot. Those embodied emissions, which are about 12% of global emissions, are amplified by the so-called time factor, how long they're in the air. It's not just the height of that line above the horizontal, it's the area to the right of the line, how long the emissions have been in the air times how big the emissions are. And those embodied emissions are up there before you even move into the building. So here's your big takeaway. If you remember nothing else, know that something you build this year, 3/4 of your climate impact, more or less, is from the materials you chose to build with. And we haven't been paying attention to that up until recently. Now there's a lot happening. I'm happy to report on that to you. But another analogy first. I was looking at the map and I can imagine that before the pandemic, you could fly around your part of the world. They probably had all sorts of little short hop flights between Detroit and Cleveland and Chicago, Milwaukee, and you'd go to the airport to get the 1220 to Chicago, and you wouldn't expect to see a 747 pull up at the gate. You'd expect to see a little prop plane that would get you there in an hour, and that was all you needed for the 20 people who are on the flight. Nobody would use a 747 for that. But metaphorically, that's exactly what we've been doing in construction, is using a 747 for everything. The way we make concrete, the way we use metals, the way we design our buildings, as if there's all the fossil fuels in the world and all the room in the world to throw stuff away, which just isn't the case. Concrete's the big one. 8% of global emissions are attributed to the making of concrete worldwide. How does that come to be? Concrete's a very low carbon material. Pound for pound, it's a very low carbon material. So how does that happen? A ton of concrete, if you work it out, is about desk height. You make a cube, you get about 29 inches on a side. But the world makes 10 billion tons of concrete every year. How big is that? I did the math about 6 or 7 times because I couldn't believe it. But you get a cube that's about a mile on a side. It's 5 times the height of the Eiffel Tower. And that's how you get 8% of global emissions. 10 billion tons of anything is going to have an impact. That other concrete, asphalt, are all our streets and highways, same sort of deal. A lot of it everywhere. We've now covered the surface of the earth, the equivalent of the size of Texas or France, with asphalt and buildings. So make low carbon concrete, right? Reduce the carbon footprint of the concrete. It actually isn't that hard. And I speak from 42 years experience as an engineer. Virtually every concrete I have worked with every project I've had, I've gotten much higher strength concrete than I needed, much higher carbon concrete than anybody needed. And there's a lot of reasons for that. And I'm not blaming anybody. It's just the way we've been operating. We've been using a 747 to do everything when we could have used a Piper Cub. So out here in Marin, we decided to do something about that. Enough with the 747s. We wrote a low carbon concrete building code amendment, and we passed it into law a year ago. And then the pandemic started. So it's hard to say how much effect that's having. But it's being replicated now in a lot of places, and the idea is catching hold because people in the industry know that we're basically making much higher carbon concrete routinely out of habit than we really need to do to get strength, durability, all the things that we want out of concrete. But there's a lot more to this than just concrete. Steel is the other big one. 7% of global emissions are attributed to steel, half of which goes into buildings, rebar, wide flange shapes, all of that. So steel's the other big target, but there are others. And one of the surprising ones is refrigerants, the fluids, the hydrofluorocarbons that make the fluids that go into air conditioners and freezers and refrigerators are thousands of times more potent than carbon dioxide. And this picture I took at my local strip shopping center is the same as behind any convenience store or shopping center. A bunch of this stuff, and it's dripping away onto the pavement with an enormous effect on the climate. A lot of opportunity there to improve. This is Cairo, where I was a few years ago, and this is residential housing in Cairo. They don't do single family houses. I mean, in Beijing. They don't do single family houses. They just don't. This is residential housing. These were going up. I was driving down the middle, on a highway down the middle of Beijing, and in every direction, several of these were in construction. It was jaw-dropping. And they all look like this. And these people are moving out of the country into the cities, into the new cities in Asia that you hear about. And if they're lucky, they get enough money to buy a window-mounted air conditioning unit and pluck it on the window, and there's their HVAC. That's about as inefficient as it could possibly be. These aren't insulated buildings, and they're dripping away from the moment they're put in. So how do we draw carbon down? We can reduce the emissions, but we also need to find ways to draw it down. Well, you see lots of pictures of things like this, devices that will pull carbon dioxide out of an airflow. This one I see all the time, and more effective are the ones that actually get mounted straight on the smokestacks of power plants and cement plants and so on, where the carbon dioxide is much richer and it's a better place to try to gather it. There's also natural ways, right? Trees and the crops we grow are gathering carbon all the time. And I was one of those who, until not so long ago, I was poo-pooing the big machines that you see in the upper right there because, oh, well, don't these guys know about trees? Well, they do know about trees, but the thing is, trees don't give us gaseous carbon. And this is a whole nother sidebar I could spend another hour on, but we do need these machines that somehow are drawing the carbon out of the air to give us gaseous carbon, because that proves to be essential to a circular economy and shaping resource flows, because that carbon can be used to make concrete, to make plastics, to make fuel, make all sorts of things. So we have to gather the carbon in a way that we can reuse it. But the plants are doing all that a lot too, and we can use that. They eat sunlight and carbon dioxide, and they turn it into carbon and store it in the soil. That's the basic process that we need to start working with. Mass timber, you hear about a lot. It's sort of the poster child for the new green architecture, for climate-friendly architecture. And it is, and it can be, but it isn't necessarily, because if you're not sustainably harvesting the lumber, if you're wrecking the forest, you're really not doing anybody any favors. This is a sustainably harvested forest that you see in the picture there, by the standards set by the industry, which is obviously not that stringent. There are better standards, and if you use the lumber by those standards, you're much better off. And you can get mass timber now in North America, and I think also in Europe, that's made with FSC, Forest Stewardship Council certified lumber. That's the answer on that one. But really the bigger future, I think, is in straw. That is what we throw away. We grow our food whether or not we're going to use the straw for anything or not. And we grow a lot of it. 2 billion tons of straw. If you turn that into the density of a straw bale, typical straw bale, it's about 1.75 miles on a side. It's a cube that looks like that. And if you turn that, half of that is carbon, And if you turn that into building products, which we know how to do, you could basically negate the emissions from all of that concrete. But I don't mean straw bale buildings, though they have a certain charm. And my little moment of jingoism for America. Straw bale construction was invented on the plains of the United States out in western Nebraska, where the settlers had nothing else to build with, no stone, couldn't even cut the sod to make sod houses. But they had newly invented baling machines, and they invented the straw bales. And some of those buildings are still there 120 years later. Straw bale construction had started a revival 30 years ago, and now it's spread all over the world. Just like democracy and jazz, our little American gift to the world. But you're not going to make a New York City out of straw bales. So what could we do? Well, straw bale 2.0, there's a world of straw products coming online now, and some have come and gone, but some are going to stay here. Straw blocks, straw panels, straw lumber, straw sheathing. The upper left is a panel company that just went into operation here in California. The lower right is a fantastic company in Europe, now starting to get a toehold in North America, called Eco-Cacon. They make very carbon intensive, meaning carbon storing buildings. It's a great technology. And all sorts of other plant-based insulation and sheathing systems are available now. People say, well, what about straw? All these things, they're going to burn, right? They're going to rot and they're going to burn. Well, if you do it wrong, yes, they will. But one of the worst fire disasters anywhere on Earth in the last 20 years was the Grenfell Tower. Some of you may have been around and remember this, about 4 years ago. And that wasn't straw. That was the plastic foam that everybody thought was so safe. It was polyurethane foam and polyisocyanurate. It was a bad design, basically. Bad design will wreck anything, no matter how good your material is. And really good design, you can make a good house out of cardboard if you really know what you're doing. So design is kind of important. So you engineers, they count on us to know what we're doing here. And these guys didn't. And a lot of people died. But it wasn't because it was straw or cork, it was foam. This is a straw bale house that went without problem through one of the recent wildfires in California, when everything around it, as you can see, burned. I'd much rather be in a straw bale house than a wood frame house in these wildfires. And all these insulation systems that are available to us now are mostly really high carbon. Remember my talk about the refrigerants and the stuff drip, drip, dripping? Well, it's more or less the same kind of chemicals that we use to make our extruded polystyrene and our styrofoam and those kinds of things. Whereas we can use natural materials, cellulose-based materials, to do the same stuff. Bamboo is having a renaissance. You can build really elaborate architecture with bamboo, but you can also make really ordinary stuff. Great company here in California, Bamcor, is learning how to turn it into panels, so it works with rectilinear architecture that we're all used to. Hempcrete's another big one coming online. Now that the barriers against hemp, is so mistaking it for cannabis or making jokes about all that. Hemp is a fantastic material, and we're growing more and more of it. And there's all sorts of stuff, clothing, medicine. And once you've taken everything out that you want for clothing and medicine and food from hemp, what's left are these tough fibers that are really great for building with. You mix them with a little lime or a little bit of cement, and you get a doughy substance that you can pack into a wall or spray or whatever. The British started it. They've done all sorts of buildings now. It's all over the world now, and it's just arriving in the USA. The US Hemp Building Association just started last year, I think, and already has hundreds of members. Great stuff. Doesn't burn, doesn't rot, insulates. The big, longer future, I'm sure, is with what I call the little ones, microbial life, bacteria, fungi, and well, what else am I thinking of? But you see things like Ecovative that makes insulation out of basically mushrooms. Spray it in with a little bit of cellulose and it fills up your wall cavity. Or Biomason in North Carolina, a wonderful woman there has invented this bacteria-based concrete that gets very strong very fast. So far, it has to be done in the factory. It can't be done on site, but still very exciting. I think she's starting to supply the Department of Defense. Lots of cool stuff with the life forms that are too small for us to see, but can do all sorts of amazing stuff for us. When you get into this stuff, you have to start learning the accounting systems by which we do it. I won't try to unpack all of this. You get product category rules. If you're going to say something has a carbon footprint, you have to know by what method and with what information you're going to make that claim. That's a fast evolving field. It's by no means mature. And so we're sort of laying the track as we go here, but we're getting a sense of how do we measure these things? How do we compare any two things? How do we know? What is the carbon footprint? How do we know where we can improve things? Until you can count it, you can't measure it, or you can't improve it. So it's a bit of the Wild West. It's still very much something in development, but it's going to be part of all of your lives who are involved with the built environment. I just threw this picture in because it's cool. A colleague of mine, who's a professor of architecture at Berkeley, he's been doing all sorts of stuff with 3D printed building. This is salt. He was determined to find ways to do 3D printing of building materials without using plastics, without using petrochemical materials. He uses salt, he uses mud, he uses waste materials of all sorts, doing really cool stuff. Here's an example of a net carbon storing building. It's not only a net zero operating building that uses less energy than it produces with its solar panels, but by using straw insulation, reclaimed lumber, and FSC certified lumber, and various other materials, this building soaked up more carbon out of the air than it's ever going to emit. That's the exciting possibility in front of us. For the next 30 years, what's it going to look like? Well, what you hear most often is zero by 2050. It's a favorite goal that you hear announced all the time by cities, by counties, by countries, by corporations, by trade associations. And it sounds pretty good, and it is pretty good. It's better than nothing. Sometimes I fear it's a little bit of rearranging the deck chairs on the Titanic kind of thing, like keeping everybody busy and kicking the can down the road and not really doing anything. So we have to be held to task. But I don't say that to blame the CEOs of the corporations or the city councils or anybody else. We're all guilty of not seeing the big picture often. We get absorbed in our own little lives and our private little dramas, and we don't remember that we are in a climate emergency, but we are. So what can we do about it? We who work in the built environment, we have something to do with resource flows. Well, the embodied carbon can look like this. You know, these numbers on the left you see there are emissions per year, and the built environment is a little about 20 gigatons of emissions per year. Embodied carbon is about 6 gigatons globally per year. What if we were to just bring that down and get to the point where 15 by 50, we were absorbing 15 gigatons per year? That's the goal that we have to aim for. Not just net zero, that's not good enough. That's just not going to be good enough. We in the built environment can do all sorts of stuff. I'm sure that not I and not any of you right now can even imagine, but in a few years' time will just be obvious of how we can use buildings in the built environment. Everything, our highways, our power plants, everything we build can be a place to absorb and store carbon. For you as a person, and for you as an engineer, for you as anybody, whoever you are, reduce your carbon footprint as best you can, for sure. But don't freak out about it. You can only do so much. You can stop eating meat, you can stop using plastic, and you can only do so much. The thing is, make your handprint bigger. My old friend Greg Norris said, it's as simple as that. Just make sure your handprint is bigger. Educate people, start a recycling program, be a better engineer, be thinking about this and do what you can to have a positive impact for the climate. That's the job in front of all of us. This is my book, a whole bunch more about all of this if you should care to read it, and I thank you for your attention. And I'll stop my share.
Thank you. Thank you so much, Bruce, for a most inspiring presentation, especially on the exposition on the approaches to reducing embodied carbon in buildings, and the challenge you gave us at the end of your talk. As I mentioned earlier, we have 3 panelists: Missy Stutz representing city government, Lionel Lemay representing the concrete industry, and Luca Henrion representing policy studies at the University of Michigan. I would like to now invite the panelists to give their response and reactions to Bruce's propositions. And please do feel free to address questions to one another. Remember what I had discussed when we arranged this panel discussion. I like to make this a lively conversation. So Missy, would you like to get started?
Happy to. Bruce, first of all, thank you. That was delightful, really exciting and inspirational. I think one of the things, sitting in the city of Ann Arbor with a goal of a full decarbonization in an equitable and just way by 2030, that we sit with is not just new buildings that may be coming online, but what are we doing with our existing infrastructure? And so I'm also really interested from the panelists to understand, how do we promote smart reuse of what we already have? How do we address the embodied carbon that's already in our infrastructure? And in a place like Ann Arbor, we might build from a city government 1 or 2 buildings in the next 10 years. We're just not going to build a lot. So that's kind of a piece of the equation I think I want to elevate, is that you're right. A lot of New York cities aren't coming up in the US. They're coming up in other places. Let's do those right. Let's fix the problem from the get-go. And I'd also just really like to hear and think about what we do with what we already have to use it the wisest way possible.
Can I respond to that?
Yeah, please do.
That's a huge and great question, because in fact, the most important thing we can do for the climate is fix up the buildings we have. So don't even build 2 new buildings in the next 10 years. Just resolve you're not going to build anything. You're going to find something and make it work. Most of the carbon in a building is in the structure and the enclosure. And if it's in at all reasonably good shape, we've got many studies now that show this. Take a building that's there that nobody wants or is underutilized. Give it an energy retrofit and adaptive reuse, is the term architects use, and turn it into whatever you may need it to be. There's going to be a whole lot of that to happen, because every downtown of every city in the world is emptied out right now, and it's not going to fill up right away. The biggest building in San Francisco, the Salesforce Tower, Salesforce moved out of. They say, oh, we don't need it anymore. So it's a really good question. Thank you. Fixing up the buildings we have, meaning giving them a good energy retrofit, far more important. And it's way better to just fix up a building than to build a new one. Thank you.
Others who wants to chime in? All right. If not, maybe I'm looking at questions coming in, and this one may be a question addressed to Luca. So the question from our participants is this: we don't have a lot of time for the normal adoption curves. What is necessary to quickly scale up the use of low carbon building materials? What policy options are there that are most effective for low carbon buildings?
Yeah, that's a great question, Bruce. Thank you so much for the talk. That was really informative. For me in this climate, I think the important thing for us to realize is that the technologies exist that can significantly reduce emissions associated with concrete. But still, for any new technology or product that tries to enter the market, you need a pronounced demand signal. And I think that policy is the sort of driver that might be able to provide that demand signal in the fastest way. The national arena where this conversation is most prominent is in replacing deteriorating infrastructure, which has long been overlooked. I looked at our ASCE infrastructure report card before this, and we got a C-, which is showing significant deficiencies that we have. Since most of infrastructure is purchased with public dollars, it's feasible to find a public policy solution to addressing this and addressing what we've coined as the sort of the twin challenges of climate change and crumbling infrastructure. And obviously shaping resource flows, utilizing and diverting industrial waste streams towards fixing public infrastructure is an important component of that work. For me, there's 3 sort of components that need to be addressed overall to make this drive forward. So first, we need to introduce the tools into the procurement process that accurately calculate and compare the embodied emissions associated with construction materials. Second, our building codes have to allow for new technologies to be specified based on their performance and allow the design process to drive down the embodied emissions. And then finally, we have to find an incentive structure that takes care of that sort of green premium that you might see with new types of technologies when comparing to a traditional Portland concrete solution. So that would be sort of an overall picture of what I think needs to happen in the policy space to address this. And obviously infrastructure being the big national conversation where this is happening.
Can I ask Luca a question and also tee up Lionel on something, which is those three pillars that you talked about, really being able to calculate through procurement processes, true embodied emissions, building codes, and an incentive structure. Let's take building codes. If you sit in Michigan, we can't have building codes more aggressive than the state's code, right? So we're a little bit hamstrung. We've got to work in that structure. So Luca, I'm wondering if you can elaborate. And then Lionel, what are you doing at the American Concrete Institute to make sure that states are adopting more aggressive building codes that allow us to do exactly what Luca just told us is necessary?
Yeah, Lionel, do you want to go first, or do you want me to?
Well, why don't you answer the first
Sure.
question, and then I'll answer the second one. Sure.
Yeah, definitely. I think Michigan's an interesting case. I know Bruce's experience is working in Marin. It's different, right? I think you have to be aware of the sort of like local design processes. I think one of the biggest things is, in conversations that I'm having with MDOT, they've been aggressive in their reduction of embodied carbon, and it's just not being acknowledged in this. It's not like in the zeitgeist that people in the AEC space. And so one of the questions has been, how do we make sure that we talk about these aggressive use of supplementary cementitious materials, which are all feasible and being used within the state of Michigan for some of MDOT's processes? How do we just get that and educate people to use these methods of reducing embodied emissions that are currently available? I think what you're talking about is definitely definitely a really good point. And I think the biggest issue that we have is grappling with construction materials is you have to sort of bring in all the different stakeholders and find a solution. That's something that we've been working on. I've had the chance to sit in on a group of architects, engineers, and building suppliers within the Ann Arbor area. And what they've been talking about is, just trying to figure out what's acceptable within sort of MDOT standards for construction, but feasible for actually really reducing embodied emissions. And how do we create sort of a best practice case that can be shared widely so that the knowledge about the ways that we can reduce that becomes available everywhere? Obviously, there needs to be sort of regulatory shifts and moving into a more performance-based approach, but it's definitely a big piece to make people aware of what they can do today.
Thank you, Luca.
Right.
Lionel, you want to jump in?
Yeah, sure. So I just want to make a correction. I don't represent the American Concrete Institute. I'm with the National Ready Mixed Concrete Association. I'm a member of ACI, though. I just want to point out that, one thing that we definitely promote here at NRMCA and even wider in the concrete industry is the idea of a performance-based approach. So Bruce mentioned, the whole process of life cycle assessment and using that process to get to a lower carbon footprint for the built environment. We believe that's the approach. Unfortunately, for decades, we've been trying to convince engineers to stop, believe it or not, and you know this, specifying things like minimum cement contents and maximum fly ash contents. And then all of a sudden, the opposite is happening. Both are really misguided. I would say that, the whole building life cycle approach is really what most of the leading building, I won't call them building codes, but the green building standards such as LEED, Green Globes, International Green Construction Code, ASHRAE 189, Envision, that handles infrastructure, all have taken this whole building life cycle approach where you basically look at all the materials on a project that go into a project and you do a life cycle assessment. You evaluate what a sort of a typical benchmark building or infrastructure project would be. Then you compare that to a proposed building with as many reductions in carbon footprint as you can achieve. And I've seen many projects that have, just for concrete, because obviously that's what I focus on, significant reductions in carbon footprint. And that's what those codes, because you're using a very scientific, performance-based approach to measuring a carbon footprint and then offering reductions, I've seen incredible reductions in carbon footprint. The unfortunate thing is when you go to prescribed building codes, including the Marin County Code, where basically you begin to prescribe what is considered sustainable. And unfortunately, what you don't get is really far-reaching reach type approaches, and you don't get innovation. Basically, what you get is, like all building codes, the worst building you can legally build. And it doesn't really drive innovation, new technologies, new materials, and so forth. And you're not going to really get those incredible reductions in carbon footprint you can get with a more progressive performance-based approach with whole building LCA.
So going away from prescriptive to performance-based design of materials. Yeah, I hear that. Yeah. So any others wants to jump in? There is a question coming in, which is related to this conversation right here. And that is, any thoughts on how to stimulate demand for the regional markets that consume regionally produced carbon sequester building materials? Who would like to respond to that question?
I'll take a shot at that, only as a sort of to just say that there's a community of us. And by the way, if you're interested in these matters, you should look up the Embodied Carbon Network. It started out of the University of Washington, and it's now thousands of people worldwide. That's the community. That's the coffee house to hang out in, to know what's happening with embodied carbon. When I was in Cairo, I was walking the streets of Cairo with this Egyptian architect, and he kept looking at me saying, "I know your name, Bruce King." Oh, he says, "You're on the Embodied Carbon Network in freaking Cairo." And that was 2 years ago. So that's where the action is, Embodied Carbon Network. And I bring it up because a bunch of us are, I'm on the periphery of this, but a group of people may win this $10 million prize, which to further carbon storing building materials. And one of the targets is to that question: how do we support regional building? How do we develop non-standard standards, if you will? Because the straw that's available in Michigan is different than the straw that's available in California. Or if I'm in the high Sierras in California, there's pozzolanic volcanic soils I could use for my concrete if there were standards by which I could work with it, and the insurance companies would feel comfortable and the building official would be okay, et cetera. In other words, how do we make the construction industry more granular and not try to keep doing this one size fits all thing with national standards, which have served us for sure, but there's a lot of problems with those too. So that's something that we're going to be working on a lot, because right now it's very hard to do something that's just on a regional basis. Usually, like most of the straw bale buildings that have been built in America, we're using this little loophole in the building codes that have been there forever, the alternative materials and methods. It's like a science fiction wormhole. It says, well, as long as you comply with our intent to keep everybody safe, you can do whatever you want. Just show the building official whatever you want to do will work. And that can be extremely useful for these purposes. And that's what people rely on right now, but it's cumbersome, and we hope to do better than that.
And if I can go off that, Bruce, there's a volunteer network called the Open Air Collective, which has been working on several strong policy solutions. They have some state level policy in New York and New Jersey looking at using environmental product declarations and essentially the lowest embodied carbons in the bidding process as a way to sort of make a race to the bottom that provides an incentive for the builder that's designing these buildings to not just meet the prescriptive minimum, but say, how do I get as low as possible so I can get this sort of discount? Another thing that they've been piloting is the open source Sidewalk project. And that's actually really interesting in addressing regional construction, because essentially what they're trying to do is find local representatives, and we're working on this in Ann Arbor. There's some people working in the river towns near the Hudson River in New York, finding what are the available supplementary cementitious materials that we have, what are the sources that we can have, and what is, for our local area, the lowest embodied carbon mix we can make for sidewalks, which you can imagine don't have a very high performance requirement, but it's a really accessible thing that a lot of people will use, and it's a really kind of a visible piece of infrastructure that people will use every day. And so that's the idea, is to sort of get local knowledge about what's available and how do we make the sort of best case scenario for each individual in different areas. And then we can sort of address that granularity by spreading that locally. Once we have the best Ann Arbor mix, well, I'm sure it'll work in Dexter, or we can spread it throughout the state of Michigan, and hopefully see that sort of cultivation of knowledge about how to lower the embodied carbon for these small pieces.
Thank you, Luca.
I would say, one of the roadblocks for concrete, at least, is the sheer volume of materials that are used. There's a reason why, and Bruce pointed this out, that concrete has a significant carbon footprint worldwide, 8%. In the U.S., it's probably closer to 1.5%, because most of the construction is going on in the rest of the world. And we have a higher carbon footprint generally here in the U.S. From other industries like transportation and industry and so forth. But I would say, because of that volume of construction, right, it does require significant material flows. So we get calls all the time from companies who have small amounts. Many of you would not consider them small amounts, but from a concrete manufacturing perspective, they're small amounts. And that's going to be the biggest problem, right? We have to have a consistent volume of source materials to continue to produce concrete. I would say, probably, in my opinion, the biggest opportunity is still fly ash. We don't use all the fly ash that's produced every year still in the coal, electric power generation process. We know it's coal power is reducing over time, but we still don't use all that material. Guess where it goes? Into landfills. Do you know how much over the last 100 years of this coal ash we've put in the ground? There's estimates from anywhere from 1.5 to 3 billion tons of coal ash. Some of that is treatable to the point where you could use it in concrete. In fact, back of the napkin calculations, probably 100 years worth of fly ash that could be beneficiated from these landfills. It's an incredible amount of volume of product that we somehow need to figure out how to use and incentivize. You talked about incentives, and I would say that's probably where government can come in, is providing incentives. We're taking what is now a real hazard for our country, these landfills, and converting those into usable products. If we can figure that out and make it economical and justifiable, then I think that's really the lowest hanging fruit. I mean, there are some natural pozzolans too, but all those natural pozzolans, typically, many of them do require processing. There'll be some processing involved in beneficiating fly ash, but it's pretty small in terms of its impact.
And in response to that, I have this gut in my stomach based on that I would not want to touch government incentives for fly ash. I do not want to incentivize the use of coal. I would much rather do what you were kind of raising, of figuring out how do we use the government creative innovative space to figure out how we move to the right kind of technologies. So I agree that if we're producing something, we need to use all the byproduct, but I don't want to make any investment in a technology that is literally killing us and in a fuel source that is destroying our planet. And so I'm not speaking as a City of Ann Arbor employee. I'm speaking as a resident right now who has a really hard time doubling down on a coal industry once again.
So it's not really doubling down on the coal industry. I disagree with that assessment. It's the fact that we have used coal power generation for 100 years and haven't taken advantage of what is a pretty valuable product, a byproduct.
I think all I would say is I don't want to give more incentives. We've already subsidized that industry so much. Why would we not be investing in something better?
Could I say something on that? Because I wrote a book on high fly ash concrete 15 years ago, and I studied this, and ever since then, I get this question a lot, along with others, like, isn't it chemically toxic or dangerous? And to that question, yes, it is. You don't put it on your breakfast cereal, but when it mixes with some cement, it becomes minerally bound and the heavy metals aren't a problem. As to whether increasing the use of fly ash for concrete, because it makes really great concrete, it's great stuff, will incent people to build another coal-fired power plant, that just seems highly, highly, highly unlikely. So Lionel was only talking about digging up the stuff we've been throwing away and making use of it, which I completely support because it's just sitting there, a toxic soup in the ground. You guys may remember Tennessee, I don't know, when was that, 15 years ago, when one of the dams burst and that stuff flooded through a whole valley. It was awful. And nobody wants that to happen. Nobody wants that to happen. The coal companies don't want that. So if we could dig that stuff up and use it in our concrete, it looks like nothing but a plus to me, but I don't think it's going to end up spurring a revival of coal-fired power. Not a worry. For many reasons, coal-fired power is going away, at least here. China, maybe that's a different story.
Okay, I think you guys fulfill my wish of having a somewhat heated discussion, but that's exactly what I was looking for. If I may change direction a little bit, we have just a few minutes left. I see a question coming in, and it looks like it's heading to Missy's direction. And the question is, when planning for future building emissions, does the City of Ann Arbor anticipate and plan with an emissions level similar to that prior to the pandemic, or have expectations changed over the last year?
Yes and yes. We do annual greenhouse gas inventories of the entire community as well as of municipal operations. And so in some ways the baseline always shifts, especially with the goal of carbon neutrality. Our baseline assumption of which we planned from was 2018, so pre-pandemic. Of course, the pandemic has shown us a shift in many things. Bruce mentioned this too, in terms of where people are using buildings. In our area right now, since the students are here, DT made $30 million extra this year, not because of increased load, but because load switched. It switched from industrial, commercial shops to residents, and residents pay a higher rate. And so we're seeing these kind of shifts. We're seeing a shift in how people move in their community. And so that will certainly inform what is possible going forward. How much is telework now a thing that it wasn't pre-pandemic? So certainly will inform the actions that we take in our emissions profile. But yes, we do emissions inventories every year to keep track of our goals.
Thank you, Missy. I save the best question for myself. I take the prerogative as being the moderator. This question is coming from a student, okay? And he's asking, how can students get involved in carbon sequestration research? And what are the academic pathways for pursuing this as a career? So I would say this, join a civil engineering program, and of course the one here at the University of Michigan. Carbon sequestration research is part of the Shaping Resource Flow strategic theme of our department. And there are plenty of research activities led by faculty members, both on the dry side, we call it the civil engineering side, as well as the wet side, the environmental side. We also, by the way, have a Center for Low Carbon Built Environment that aims at lowering carbon emissions of the built environment by 50% in the next decade. Our goal is to bring together the various stakeholders from industry, from foundations to government, and academics to try to solve this carbon problem, climate change impacts problem as quickly as possible. So I would say to the student who asked the question, yes, this is a great career in carbon sequestration research. It's going to be very satisfying to you if you pursue this direction, but also a direction which I believe would lead to meaningful impacts on society. And so definitely I would encourage you to do that. Okay, so just to wrap up, I see the time is hitting 2 o'clock today. I'd like to invite the audience today to visit our website, the University of Michigan Civil Engineering Department website, particularly umservicetosociety.org. Service to Society in one word. This is the site that allows you to explore a bit more about our departmental strategic directions and also register for future events in this distinguished lecture series. So I wish all of you a great day, and I want to thank Bruce and the distinguished panelists one more time. Thank you so much. Have a great day. Bye-bye now.